Thank you. Can you hear me? Okay. This guy has a problem, and this problem has to do with Python, because basically this guy has just learned Python, maybe 1 or 2 years ago, and he tried it with small snippets of code, and everything was, oh, yeah, works very well, very fast, much faster than C++, I can be more productive, and then he tried to start doing production with it and try to make, instead of small snippets, some medium-sized program. And then he found out that, yeah, works very well, but these abstractions sometimes leak. And then you have some memory leak somewhere, and your program has 2 gigabytes of RAM occupation, or is a little slower than expected, and it doesn't know how to solve these problems. So if you are kind of in this situation, this is the talk for you. If you are like a 10 years Python core committer, and you develop half of C Python, then probably it's not the good talk for you, okay? Just a short introduction, but actually Valentino already introduced myself. I organized PyCon Italy and EuroPython. This is what I'm mostly proud of. And I'm CTO of Develer, which is one of our sponsors. And these are my Twitter and blog reference, in case you want to follow me in the next few years, maybe. Okay, so this is the roadmap of my talk. We will look into memory leaks first, and resource leaks in Python in general, which is actually a big topic. So we will detail what is a memory leak in Python, since it shouldn't be a memory leak, right? So what is a memory leak, and how we can debug it and fix the problems. Then we will look into Python code profiling, so what Python has to offer to help developers profile their code. And then we will look into C++ extensions, because all those nice extensions is like import anti-gravity, and then you fly. But sometimes that anti-gravity stuff written in C++ can, crash on you with a big seg fault, which is something a Python programmer is not used to. And so we will look into how to debug those C++ extensions, especially under Windows, which is not exactly the most friendly debugging environment for this kind of task. Just a notice, we will focus on C Python mostly, almost exclusively. So if you are like, if you only use Jython, this talk will not help you much, probably. Okay, let's start. So what's the difference between a memory leak and a resource leak? Well, technically, they should be different, because a memory leak basically means in C terms, it's a malloc without a free. So you just allocate a piece of memory and you don't release it. Okay, this should be a memory leak. A resource leak is when you lose a resource that you get. So for instance, you open a file and you don't close it. That's a resource leak. Okay, you open a socket and you don't close it. But in Python, this kind of leaks are actually coincident, because the way you allocate memory in Python is through objects. So when you need a buffer of memory to do something, you probably go through an object. So what can happen is that you leak that object. And the same happens for resources. So you open a file through an object, and then somehow you forget to call the close method on that object, and that's a leak as well. So basically, since the cleanup usually happens through either object destructure, so for instance, you have this under_del method we will analyze later. You have this method that should be automatically called for you when the object is you are done with, and it invokes the close method of file. Since you have this mechanism, you shouldn't have any leak, right? But still there can be problems in that. So still, basically in Python, it's mostly the same thing. So we will focus on how basically you lose tracks of object, and they somehow manage to still be in your process memory. But in Python, as you know, object collection is supposed to be automatic, right? So basically the idea is that Python knows the references among objects and should automatically collect objects when they are not used anymore by your program. That's the idea. So what is an object leak? An object leak, a resource leak, is when basically an object is logically dead for you, which means you don't need it anymore, but it's still not being collected by the interpreter. So we call it object leak whenever you think that you are done with an object, but CPython doesn't agree with you. Okay? So basically, this can happen for several reasons. For instance, there could be some lost or hidden reference. So in a way, you think that you have removed all the references from these objects you don't need anymore, but instead there are some hidden references somewhere in your program, and so those objects are still alive. Or obviously there could be some bugs, because Python is just, CPython is just a C program, can have bugs, and extension, C++ extensions that many Python programs use can have bugs as well, and with the bug you just maybe lose a reference to an object. And also there are some bugs in the Python core, or even if they're not bugs, they could be quality of implementation, something like choices made by the Python core that in a way affect the way your program works. I will explain this. So let's start. How do we see how many objects we allocated in Python? We use this function. This function is in module GC, which is a standard module of the Python library. This function is very nice because it gives you a standard Python list with all your objects in it. So it's just a way to get a list of all the objects the CPython interpreter knows about. But of course, having such a big list, it's probably not very useful, but there are still some nice things we can do with this list. So for instance, the first thing that comes to mind is that you can do some kind of before and after check. So what I mean with before and after check, I mean just you get a list, compute some statistic on it, then you do an operation, and then you recompute the same statistics on that list. And if you think that nothing more is being created, for instance, that your statistics should match, and if they don't match, probably there is something that has leaked through. So for instance, if the list grows, there are more objects in your environment. If you think that before and after the list should have the same size, but it doesn't, it means that what you've done between has leaked some objects, okay? Yeah, there is enough contrast. Can you read this? Yeah. So this is an example. I define a function I call howMany, and I pass it a class type. Okay, this function just goes through the GC list, get objects, and simply counts how many objects of a certain type there are. Okay, so you see I just filter the list basic on the easy instance check, and then I just compute its length. Okay, so for instance, there is a dummy class A, and if I just count how many A, it tells me 0. Then I allocate 1, how many A, 1. And then I remove a reference through del, the del statement, del small a, and then there are no more a's in my environment. So how many a's? It's 0. Okay. So another way to explicitly check for references is this function, which is in the sys module. It's called getRefCount. GetRefCount basically gives you the number of reference to an object. Number of references to an object. So if I say getRefCount A, it will tell me how many references there are to that object. Okay? You see the -1 I put. It's because when you enter that function with your code, you call the function execute. The function itself needs to get a reference to the object that you pass it. Okay, so there will be always one more reference returned by the function, because the function itself is holding a reference in the moment it counts them. Okay, so you need to decrease by 1 the count to make to get the number you need. So, for instance, one thing you can try is to check the reference count just before your logical destruction. So what I mean is that you have an object in your hand, and you are going to remove the last reference to that object. If you want to make sure that it's really the last reference, just call getRefCount. Because if it returns 2, -1, it's 1, that reference is your last one. But if it returns 3, there are another reference in your program. Okay. This function can also be used in test suite because, for instance, you can do an automatic test that checks how you use an object, and you can use getRefCount to check if all the references are being collected, and then your test will fail if something goes wrong. And if there is a reference missing, how can we find it? If there is one more reference and we don't know where it is, how can we find it? We can use this other function, back to the GC module. It's getReferrers. GetReferrers gives you a list of all objects that hold the reference to the object you pass to the function. Okay? You can actually pass a list of objects, and it will give you a list of all objects holding a reference to all those objects. Okay? We are thinking of direct references here, because here these are the references that the CPython interpreter sees. With direct reference, I mean that, for instance, in classes, in instances, you know that there is a dictionary that holds all your attributes, okay, which is the under-dict of the instance. So, for instance, if I ask for the referrers of an object which is held as an attribute in another object, this function will return the dictionary instance of the object, okay? Because that's the direct reference to the first object. So we probably need to recursively analyze the references. I have some example I can show you. So get back to the ADummy class. I allocate two different instances, A1 and A2, okay? I check I call getRefCount on A1 minus 1, and I get one reference, okay? Because there is one reference to A1. So I say, what is this reference to A1? I check it with getReferrers here, and I use prettyprint to see who's holding a reference to A1, this one reference we see here. Who's holding this one reference? And I get this, you see, it's a list here, of just one item, which is a dictionary. So there is a dictionary holding a reference to A1, and you can see the reference here, A1 main A instance, okay? This is the reference to A1, the only reference. And this dictionary is basically just the interpreter dictionary, okay? It's the dictionary that holds all the objects available at the interpreter level. It's the globals, okay? You can check it. So what I'm doing here is asking who's holding the references to A1. The first one, the dictionary, is globals, and that's true, okay? So this is the global dictionary, which is the dictionary you modify when you create something in your interpreter. You say A equal to 0, you are adding A to the globals dictionary of your interpreter. And this dictionary is always available because it's also available through the sys module. Basically, if you call this weird stuff here, sys.underGetFrame function .flocals, this is like a magic formula you can use, and will give you a reference to the dictionary holding all objects in your local context, okay? So if you call this magic formula within a function, it will give you a reference to the locals dictionary, okay? If you call this magical formula in the global context, it will give you a reference to the global function, okay? Just to show you some stuff within the Python interpreter, which is usually not very famous. So now let's just change something here. You see on the third line, I'm just adding a reference from A2 to A1, okay? So now A2 holds a reference to A1 through that XXX attribute, okay? So when I ask again who's holding a reference to A1, I get 2, because 1 is the globals dictionary, and 2 is this reference I added here, okay? Is everything clear? So we have two references to A1. If I again ask the garbage collector to give me all referrers, I get a list of 2 items. The second one, again, is the global dictionary we saw before. The first one is another dictionary, okay? But what we did is just put A1 within A2, and what I get is not A2, but I get a dictionary. And this dictionary is the instant dictionary of A2. You see? Here it's true. So what it means is that when you add an object, you add the reference to an object within another object, what you're doing is putting that object within the instance dictionary. So if you ask CPython to give you a list of all the objects holding a reference, you don't jump directly from A1 to A2, but from A1, CPython sees the instant dictionaries of A2. And this dict here, if you get the reference of this dictionary, you get A2. You see? So basically, probably the programmers doesn't want to care about this dictionary. He would like to have an easy way to see, to tell CPython, okay, I have this A2, who's holding the reference? I have this A1, who's holding the reference? A2. But you don't get this answer straight. You get first the instant dictionary, and you need to do another question to get to A2, okay? So it's two jumps. Okay, so this is just was an introduction to see how references work in CPython. And then we see how we should go to collect all this stuff. So CPython uses reference count. This is probably all Python programmers are aware of, something like that. With the reference count means that you have CPython keep tracks of how many references there are. So when this counter goes to 0, it will delete the objects. Okay? In CPython, when the reference count goes to 0, the destruction is immediate. So it's not like Java when there is a background collector going on. But in this case, we are thinking of reference counting. So when an object goes to 0, it's immediately destructed. And you can trust this feature of CPython. It's not going to change anytime soon. I actually had an argument with Guido a few years ago. Because I actually, in my own coding style, is that I like to rely on this feature of CPython a lot, which is, it's not portable among Python implementations, but since I mostly use CPython, I still like to rely on this. For instance, if you delete explicitly a reference to an object through the del statement, which is the way you explicitly remove a reference, if that was the last reference to an object, there is an immediate destruction of that object, okay? You can trust that as soon as the del statement is finished, the object is already gone, okay? You don't need to wait for the function to exit or whatever. It's an immediate destruction. Also, on function exit, when you exit from a function, all local variables are immediately destructed because the locals dictionary is collected, and then all the local variables, if there are no more references to them, they are immediately destructed, okay? Not after a while, immediately when the function exits. So either at that time or there is a problem, okay? If you target CPython, like I do mostly, you can probably try to rely on this because it's not going to change. Even someone doesn't agree with this. So for instance, if you see the 2 code snippets above, they are not, that kind of coding style is not Python, how can I say, cross-Python compatible. It doesn't work on all Python implementations, but it works on CPython. So in the first one, a read file, you see that I open a file and then directly return the contents of the file. Okay, there is no close statement, but the file is closed immediately when the function exits. Okay, so if this is probably what you do because you're just trying to read the contents, so it's open, read, close. Okay, this is what you do what you want, but if you write code like this, you can be sure that the file is immediately closed. So you're not like leaking a reference or maybe delaying destruction to an unspecified time in the future, the file will be closed immediately when the function exits, okay? And so you can shorten it even more. Second example above, okay? Also, that kind of code is correct in CPython. And with correct, I mean that the file is open, read, close, okay? Guaranteed. There are absolutely no leak, and there are absolutely no delay in destruction, okay? The formal, yeah, sorry? If it throws an exception, oh, are you asking for Python 2 or Python 3? I'm not sure. So basically, I will reply in Python 3 because the answer you will like most. So basically, what happens is that if it throws an exception, you will catch the exception at a certain point, because otherwise, if the program exits, you don't care anyway. So you will catch an exception. The file is still open there until the except clause finishes. When the except clause finishes, so you just accept accept IO error or something. You just print error log whatever, and then you de-indent. In the moment you de-indent, the file is closed, okay? This is Python 3. In Python 2, it's a little bit worse than that. You need also to exit from the function where you grab the exception, okay? In Python 2, you need also to exit from the function. There is a reason for this, but I would need like 10 slides to show why. So I don't have those. Here, the code snippet here are the formally correct way to do it in all Python interpreters. So just a second, you either try finally, use try finally, okay, or you use the with statement, okay? The with statement also guarantees destruction, and this works across all Python interpreters, even those with garbage collection and stuff, because the with statement says explicitly what to do when the block finishes, which is to call the close function, okay?
I just recently had to change my code to the right lower version, because if you run the right upper version on PyPy, you will run out of files.
Yeah.
So use the lower right one.
Yeah.
This is the best one.
Yeah, this is what I was saying before. If you target other Python implementation, for instance, PyPy, you cannot use the above examples, because in PyPy, the garbage collection might work differently, might not to use reference counting. So this one is the correct version for all Python versions, okay? So if you plan to use PyPy, sometimes, or you want to be future-proof, you don't know what to do, but maybe PyPy, so you can write code like this, and it will work on PyPy. But if you write code like this, it works already in CPython. Why I stress this? Because I need to explain you when there is a leak. So first, I need to make sure that everybody is aware when there is not a leak, okay? Because otherwise, it's all kind of magical. Those references go away sometime in the future, and we don't understand, okay? So in CPython, this is correct because the file is immediately destroyed, okay? So this is just a diagram showing the timeline. This is a timeline from top to bottom of the screen. So for instance, A object is holding a reference to B object. The one between parentheses means that there is one reference to B, okay, which is the reference held by A, and B is holding a reference to C. So if we drop a reference from A to B, that thunder, how do you say it? This sign here means that you are dropping a reference. So what happens is that the B reference count drops to 0, and then the object is immediately destructed. When it's destructed, by consequence, the reference to C is dropped, and since it was the last reference to C, you see, also C is destroyed. It also gets destroyed by the interpreter. So at the end of the day, C is collected, then B finishes his collection, and then you are left with A, okay? So reference cycle, can you see those thin lines here? Very thin, sorry. This is the problem with the reference cycles. Here there are some objects, there are these lines, so you can trust these numbers between parentheses if you don't see the lines. So, but the idea is that you get this A object, okay, and this A object has a reference to B, and then there is a complex web of references. You drop a reference from A to B, and this is supposed to work, right? But what happens is just that B goes to 1, and then all those web of references make it so no objects have a 0 reference, because they all reference together in a circle, you see? So even if you drop your last reference to this and to all this world, and you say, okay, I'm done with, go away, they still stay alive, because there is a reference cycle, okay? So the reference count mechanism failed in this example. So what Python does to fix this problem was introduced in CPython 2.0, is the cyclic garbage collector. So there is a garbage collector going on in the background. You probably heard of it. But it's important to see that this garbage collector is only responsible for collecting cycles of objects. So back to this example, the garbage collector will help you collect only this cycle of objects, okay? Because this is where reference counting doesn't work. For everything else, there is reference counting. When there is a cycle, the garbage collector, it kicks in always, but when it sees a cycle like this, it will collect it, okay? To collect this kind of cycle, it basically breaks references at random, try to get the counters go to 0 so that the object can be destroyed, okay? This is the way the garbage collector works. There are 2 phases. The first phase is finding the cycles. Okay, let's say it found a cycle. It will just get a random object, get a random reference, and just break it. So if you have some object, it's something like you say random statement like del a point x. Okay, it will do something like that, and then hope that the references go down one at a time, and then all objects go away. Okay, you can force an invocation of garbage collector through the gc collect call. Okay, this is a way to force garbage collector to happen now, which is very cool for debugging. And you can disable and enable background garbage collector, which is very useful when you're doing a lot of allocation or deallocation. So when you have this big application, which is file, open, load file, you can disable garbage collection while the file is loading, because you are allocating tons of stuff, and then you re-enable it at the end, because otherwise the garbage collector kicks in many times during loading, and you don't probably want it, okay? And this is probably a really nice speed up, which is free for you. So how the garbage collector works, I have this small animation or something like that. So this is the example before. A is our word. We lost the last reference. There is a cycle. The garbage collector starts and just drops a reference. Okay, so just say del b.x, which is C. So remove this reference. Then C goes to 0, and then brings away 2 other references. Okay, but still, no other objects go to 0. There is a smaller cycle, subset cycle of the cycle before. So again, garbage collector kicks in and says like del e.x, which is D. The references go away, some objects go away, another small cycle, third run of garbage collectors, removal of this object, again, and everything is done. Okay? Actually, I said the third run, but it's not correct, because it managed to understand that it still needs to, like loop on itself until it's done. Okay? So it just is basically just 3 steps of the one invocation of garbage collector. Let's try this in the real world. Again, A1, A2. I create a cyclic reference here. Cyclic reference, you see? A1 reference to A2, and A2 reference to A1. So we have a loop here. If I ask how many A instances there are 2 instances. You remember that how many was filtering the list of all Python objects. Okay, so there are 2 A instances. I delete A1 and delete A2. And when I do this, I think, okay, I get rid of all my references to A1 and A2. They should be collected. Yes, but not immediately. How many A? It's still 2, because the reference count mechanism here fails, because of the cycle, okay? So immediately after this statement, there are still 2 references. Then you run the garbage collector once, and it tells you that it's collected 4 objects, okay? And there are no more A's after the garbage collector. Those 4 objects, anybody has an idea why there are 4 objects being collected? It's the question? Okay, yeah. It's basically A1, N2, A1 instance dictionary, A2's instance dictionary, okay? So it's 4 objects being collected. It's written on the slide. Oops. Yeah, very smart guy. Yeah, you were smart. You were smart. Really smart. But also GC doesn't work in some cases. For instance, it doesn't work on objects with finalizers. So if you have an object with an under del function defined, the GC doesn't work. And why it doesn't work? Because it cannot break references in random order anymore. Because when you write your nice under del code, you expect that the object is in the state it was just before its destruction, right? But if the garbage collector has destructed has removed objects from, references, attributes from your objects in random points, if it invokes the del code, your del code, maybe some attributes are not available anymore because the GC has to remove it at random, as we showed before. And then your del object could raise an exception, attribute error, okay? So this is something that GC tries to avoid, and so it just cannot work with objects with the under del function, okay? In this case, you really have a leak, okay? In this case, those objects will never be collected and will stay in your process memory forever, okay?
Complex cycle and only one of the elements has a del method. Could you try to break another?
Yeah, the garbage collector, you mean? Yeah. I will repeat this question by going to the next slide. We'll explain. So basically, as I'm writing here, you can still use del on leaves. To explain this, I have this diagram here. So basically, if you have a cycle, okay, this green stuff are the objects with the finalizer. Okay, the blue one don't have any finalizer. So if you have a cycle like this, you have a leak. Okay, but if you have a cycle like this, you don't have a leak. Because in this case, garbage collector knows that it can break the cycle at any point and nothing weird happens because these objects, it doesn't touch it, okay? So because it's not part of the cycle, it's not technically part of the cycle. The cycle is holding this object alive, but is not part of the cycle, okay? So since the garbage collector only works on cycles, it doesn't see these objects, basically. So it doesn't see these objects, just see these objects, say, okay, there are no finalizers, let me just break stuff here, and then everything goes away, okay? If you have something like this, you have the leak. So what you can do is you can try, if you want, to use del on leaves, on classes that you know that will never be part of cycles, because basically are just leaves. So for instance, just to have an example, let me say you are wrapping some open, close, lock, release kind of APIs. There are better ways to do it with statement, whatever, but just to make an example. You have wrapping some lock, release APIs into an object. Okay, so you're just wrapping it, just creating a small object. Okay, this small object, you will hold some references to it, but this object will not grow some kind of cycles or web of references. On that object, you can probably use del. This is an example with OpenGL. OpenGL is a C API, okay? For instance, there is an allocator, the allocator of something called display list. You don't need to know what it is. You can do, there is this API, GL alloc list, and then GL free list, okay? Just calls to OpenGL. So you can, this is a small wrapper for making Python code fun, more fun. So basically, you just allocate a list in the constructor and free the list in the destructor. In this case, this is probably will never be part of a cycle because this is the whole class. Will never hold a reference to another class and be part of a cycle. So here you can use a finalizer. Okay. gc.garbage is a list of all the objects that cannot be collected by the garbage collector. So these are your memory leaks. You have a list of your leaks, which is funny for a C programmer. Oh, if I have a list of leaks, why it's a leak? Yeah, is it a leak? Because they will stay in this list, okay? So they are still in your process memory. You can look here if you have troubles. So if you think your process memory is growing, why don't you just print this list? Because if it's not empty, you have a problem. How can you finalize objects without using del? There is actually a trick, and the trick goes through use the weak references. The weak references, how many people know what a weak reference is? Okay, so basically it's a reference to an object in a way that it doesn't increase the reference count of that object, okay? It's a weak reference. So it doesn't really have a reference, and if the object dies, the weak reference automatically turns to none, okay? And the weak references has a nice feature. They have a callback function that you can register when the object dies, okay? And this is a way, and through this you can probably emulate del. So back to the example, GL unlock list, GL free list. This is with del. You can see how many GL display list, 0. I allocate 1, how many? 1. I delete that object, how many? 0. Okay, so everything is working correctly. The del is being invoked. How can I rewrite this without del? Like this. Okay, so what I do is that I create a weak reference to self, which is the GL display list object, and this is the callback function that will be invoked when GL display list object is being destroyed. Okay? So when it's being destroyed, the weak reference will invoke the callback function, and in the callback function, I will just call the GL free list function. Okay? So I'm basically getting the del code and moving it into the callback. Okay? But alas, it's not that easy. Because if I try again, it kind of works, because I allocate the GL display list, then I delete it, but there is still one instance of GL display list. After I call gc collect, then I get rid of that instance. So basically, it kind of works, but it delays destruction to the garbage collection. And this happens because there is a reference cycle. The reference cycle in this code is probably hard to see, because you say, oh, where is the cycle? I cannot see a cycle here. And the cycle is basically this one. You have your self object, okay, so the instance, I call it self, has a reference to weakref, right? Self.undervar, this is a reference. So self is a reference to weakref. Weakref holds a reference to the callback function, because it needs to call it, obviously. And the callback function has a reference to the nested scope. The nested scope is the scope that basically is hidden by the interpreter, and it lets you access init local variables from within this lambda function. You see that within from this lambda function, I use self. And how can this function have a reference to self? It's because this function is holding a reference to a secret list of objects, which are the objects of this init function. And this is the nested scope, okay? And the nested scope is the one with the reference to self. And this is why this lambda function can work, because there is a reference to this nested scope. So it works, but there is a quality of implementation regression, because before it was being collected immediately, now we need to wait for the garbage collection. To fix this, there is a little trick, which is to use the default arguments. you probably are aware that in Python default arguments to function are a little weird compared to other languages because they are evaluated the moment the function is compiled, or it's not compiled, but anyway, the moment the function is compiled and not at any invocation of the function. So if you just get a reference to self.id here when you create the Lambda function and you assign to ID, so basically this Lambda function doesn't need a nested scope anymore because it doesn't access anymore anything outside itself. It just calls a global function, okay, and then just use this ID default argument. So it doesn't have a nested scope anymore. There is no more access to outside references. It's just self-contained, a normal function, self-contained function, so there is no more nested scope. In this case, you don't have a cycle anymore, okay? And so this code behaves exactly like with the original finalizer, okay? This is a virtually perfect substitution for del. I was discussing this with Raymond Hettinger at some few years ago, and he proposed to. He was starting to propose this function, a finalize function, where you basically you register a finalizer. So you basically say, okay, when this object dies, I want this callback to be called, okay? And this function will basically create the weak reference for you, hold it into a registry of weak references, so that it's easier for you. Again, the display list example, there is no more weak ref or stuff. You just need to call finalize self and pass the finalizer function. But you still have the nested scope problem, okay? But you don't have to hold the reference in your object, and it's probably cleaner for you. Another small tool you can do, I always use this one, which is debug def. I pass it an object. Basically, I want to know when the object is destroyed. So I write debug det O, which means please print a statement to the standard output when O dies. Okay? And it will finalize. Basically, you see, you register a finalizer for O to a function which just does a print. Okay? Which is nice because when you're debugging, you probably want to know when an object dies. So you just say, okay, please let me debug when this object dies. Okay? And the nice thing about this function is that it works for any object. You don't need to add the finalizer to the object, modify its code. You can do it externally. Okay? Okay, those are the leaks, where the leaks in the, you mean Python side. We can have also leaks in the C++ sides. So for instance, in C++ code, the programmers need to call incref and decref explicitly. So they need to explicitly increment the counter when they start to keep a reference, and decrease a counter when they're not holding a reference anymore. If they forget to call decref, it's a memory leak. You probably are just using the library, but you have a memory leak. The API is bug-prone, but because it's bug-prone, I mean, it's just a little hard to write. You need to pay attention. I usually suggest to trust binding generators more. So if you have this random GitHub library, you found that you're not very sure it's mature, and that it's got a lot of manual C Python API code, I wouldn't trust it fully not to leak any object. While if it's using some kind of binding generator, like Cython or Swig or SIP or whatever, then probably there are no bugs, because the binding generator takes care of these reference counters, and the code is more mature, okay? I will just have some water. Sorry, I just need the microphone because I cannot hear correctly. I'm not sure if I understood the question.
If you use something like Swig and the interpreter goes down, basically you exit the program. You have the problem that modules get destroyed and the globals get set to none. And Swig usually carries around reference to a global to destroy its local objects. So if you use binding generator, you usually get a ton of those errors on program exit if you do a bit more complex things.
To be more precise, if you use Swig, you get
Yes.
ton of errors. Yeah, I hate Swig.
Okay. So it's not.
But
in
yeah,
general.
no, it's not. I mean, it's not foolproof. That's correct. But I see those extensions which are like 1 billion of code of Python CA API with the 10 users in the world, and those have memory leaks for sure. If you Swig, probably most of the code works, but Swig have some issues, large issues.
Okay, thanks.
Okay. Some code profiling. This is just basic stuff, but still gives you an idea of how to profile your Python code. The first and most simplest way to profile your code is to use the timeit module, which is a way to do just measurement of code speed. It's useful from small to medium code snippets, and basically measure the average execution time. You can use from command line. You just need to say Python -m timeit, and then you can pass one or more setup statement, which means you are set up in the environment before doing the profiling, and the setup statements are they have a -s in front of them, okay? And then you pass it one statement that you one expression that you want to evaluate, or is it a statement? No, it's a statement. Yeah, no. Oops, I'm confused. It's either a statement or expression. I just can't remember right now. But anyway, you pass it the code that you want to profile it, like this or like this. So for instance, here I'm saying, okay, Python -m timeit. So I want to do a time measurement. The setup is creating a list with just one item, which is 0, and then I want to know how long it takes to the interpreter to multiply this 100 of times. So create 100 of items with value 0, okay? This is more complex, but it can be in your application. You just import the core of your application, then you load some large data set, load foo.dat. So you see this statement, setup statement are executed in order. You load your large data set, then you find some items within these large data sets, and then you do some complex computation on them, and you want to know how long it takes to do this. This is supposed to be used for stuff like, I don't know, maybe less than a second or not 2-3 seconds. If it takes like 2 hours, it's not the right tool. The nice thing is that timeit has dynamic precision. So it works from microseconds to milliseconds because it adjusts dynamically and knows how many times to retry executing your code to be sure that the error that it gives you from the average is correct. So, for instance, this is an example from PyQt4. You can just measuring how long it takes to a Q matrix to be inverted. Okay, so this time it automatically decided to try to do this 100,000 of times, so that it can give you an idea that it takes 5.93 microseconds per loop. Per loop is executing 3 times. Okay. This is nice because you can use it to compare different implementations. If you just tweak something, you want to see if it's really faster or not. Maybe you went to some Raymond Hettinger talk where he was saying like, oh, you can like do this nice thing with the dictionary. If you use pop items, it's faster than doing nested a list comprehension, something like that. You want to know if it's really sure for your code with your data set, then you can try to compare implementation with time it, okay? Microprofiling. For large profiling, there are two main types of profiling. You can have deterministic profiling or statistic profiling. Deterministic profiling means that your code is instrumented automatically. So basically, the CPython interpreter has a way to know exactly when a function begins or ends and measure the time. Statistic profiling means that basically there is like a check very often. So it basically schedule a timer and say every, 10 milliseconds, and checks in which function it is at that point. And then by statistics, it says, okay, this function takes a lot of time because many times when I wake up, I was within this function, okay? So you can either have the statistic approach or the deterministic approach. cProfile, it's not really hot new right now, but hot new is the hot new guy. So you can basically, this is the module you want to use for, your day one profiling, just use cProfile. cProfile, this is an example on how to use it. You can use it from within your program or from the command line again, like time it. So I have this testful function that I want to profile. I call import cProfile, cProfile run. To cProfile, I need to pass a string, which is the statement to profile, okay? Which is the way to, it's just a trick to delay evaluation of the function. I need to tell to cProfile what to do, so I pass a string, it will exec it, okay? And will measure it. Or you can do it outside, so if you have a program that does testfoo, you just can do python.m cProfile foo.py, okay? And it will measure how long it takes to foo.py to complete, and where the time is being spent. And this is what you get from cProfile, which is a big nightmare of numbers. The first line shows you how many function calls there are, because cProfile is only, and also profilers mainly are focused on function calls. So they don't give you an idea of what happens within a function. So if you have a big function and you don't know if loop 1, loop 2, or loop 3 is the one taking longer, you need to split it into different functions before running cProfile, because cProfile will give you information only at the function level, okay? So you say there are 389,000 function calls in 2.6 seconds. Keep in mind that time, this is not the real running time. It's the running time within the profiler, which is much slower than the real running time, okay? But it's still printing it, because if you change your code, you can still compare it, okay? Because relatively speaking, it's correct. Then if you want to know exactly how long it takes, you need to run it outside the profiler, okay? Then you get this table here for each function. So I get this Voronoi connected function here, line 78. This is in line of your code. You know how many calls to that function, how long does it take in total to run the code, how long a single call took. Then there is the cumulative time and the per call time. We'll explain this. But this table probably needs some sorting, because obviously you get a big dump of all those functions, but you want to sort them to focus on the main bottlenecks. So the main two columns that you want to sort against are cum time, which is cumulative time, which is the time spent within a function without its children. Okay? With children, I mean function being called within that function. Okay? So you want to know how long it takes for the statement of that function to execute, excluding function call, nested function calls. Okay? And total time instead is the time spent within a function, including all the children, so until the function exits. Okay? So to sort by internal by cum time or tot time, you have to use this -s command line, which is also a sort keyword argument to the cprofile run function if you are debugging within your code. There is, I think there is a mistake in the slide actually, because actually this is cumulative, internal is tot time. Sorry, this is inverted. So the column called cum time is actually the cumulative time, and the column called tot time is internal. Okay, sorry for the mistake. This is the problem here. I got confused because there is a clash. They should use the same word, command line and column, but they don't use the same word. So, for instance, here I'm sorting by cumulative time, which is function with all the children. So the function that takes more time to execute, cumulative, it's the main. Okay? Because the main entry point of your program is the one that, including all the children, takes most of the time, because obviously it stays alive until your program exits. Okay? And then there is probably the main is doing exec file, and but still, if you find a function like this RP, which it was not expected to be the one to take most, you can find it very high in the code. You can have a look at this function because it's probably slower. So when you sort by cumulative, probably the first few entries are not very significant to you, because are the main points, main entry points of your code. But then you just need to go down in the list. You can probably find something interesting. This function is invoked 100,000 times. So, okay, cumulative time is almost, 90% of execution time. You see, this is the total execution time, 1.8, 1.58, only in this function. Okay. Internal sorting. So here I'm checking how long it takes for function without children's. And I found out, for instance, that in this example, since it was an example, I was generating a lot of random data. And the round range function was the one using more time internally. Because it was doing the algorithm for random numbers, it was the longest. Okay? So the idea is that when you profile the code, you get lots of numbers back, and you want to analyze these numbers. It's not enough just to have a quick glance, because the numbers can confuse you, can confuse anybody, of course. So the idea is that you probably want to do more profile sessions. I suggest you to always try different profiles as well. Try cprofile and hotshots, because cprofile can instrument your code in a way that somehow create overheads in points that hides the real bottlenecks in your code. So it can happen. So try both cprofile and hotshots for statistic profiling. Try different data inputs, of course. This is basic profiling stuff. If you debug only against one data set, you probably fix everything in that data set, but this is not what you want. You want your program to work well on average. Okay? Also pay attention to overhead and absolute numbers. So numbers within cprofile are always increased by overhead, as I was saying before. So if you just lose focus, you are really profiling, you're shoving off a lot of time from your function, and you go down to optimizing that code, taking 0.05 seconds, but it's 0.05 under profiling. So maybe at real time it's really nothing, it's a wash. Okay? So make attention not to trust too much absolute numbers. Use profile to compare relative numbers. Okay? The numbers relatively. And time.time, it's a way to get back to reality, because you just use time.time, print to standard output how long it really takes for that code to execute, and then you can scale back from your profile numbers that maybe you saved and get back to reality, to the real execution time. Sometimes profiling is not enough. You don't see anything glaring. You think that it cannot be optimized further. Okay. So what you can do is split into multiple functions, which gives you more visibility, as I was saying before. Or you can try a C-level profiling, because maybe the overhead is not really in your code, but within your your extensions. I suggest to use OProfile. I suggest to use OProfile on Linux, which is a really nice tool. For instance, a few years ago, we found out about or upgrading from PyQt 3 to PyQt 4 using the very first early versions of PyQt 4. The application was slower. We were debugging and looking with cprofile everywhere, and there was nothing showing up in the profiles. So we were wondering why it was getting slower. And it was actually a regression in the binding generator code. The binding generation code was slower, but since it was spread among all objects creations and destruction, you just didn't see it because the numbers were higher than before, but everywhere. So you don't see them at the Python level, okay? Every single object creation, object destruction was taking a little longer. But totally the application was like 3 times slower, okay? So that's the problem. You didn't see anything in the profiling, and you just run OProfile 1, and you see that single function at the C level using 80% of time, okay? And it's within the binding generator, and then you realize that there's something going on there, okay? I was saying before, don't lose focus, okay? So macro optimization, don't pay back. Make attention not to lose focus and not to focus on details. When profiling, it's really easy to lose focus because you see all these numbers. You are following this number. You think that this function, because it's a bigger number than this one, it's most important, but probably it's a wash in your code, okay? You can use the pstats module to analyze data post-mortem, let me say. So basically, you can just run something across your night, save the data to disk. A cprofile can save data to disk with the -o, or you can pass the output file. And then once you have your data on disk, you can load it back. You can load with the pstats and do all the sortings, okay? So that you save your profiling data and analyze it, so that you don't need to, rerun it just to change the sorting or stuff like that. If you want to have some, just a quick hack to try speeding up something, I suggest to use Psycho first, or PyPy you can try nowadays. You can try PyPy on your code if your code is like mathematical code or something like that. It doesn't have many C extensions or something like that. Probably PyPy could give you an exception, an improvement because of the just-in-time code. Psycho as well you can try. These are, I wrote 10 minutes, but probably a couple of hours you can try PyPy and get an idea if it works on your code. I also suggest to use Cython, which is a very nice tool. So if you have this module, which is too slow in Python because it does a lot of computation or something, you can try to convert it to Cython. It's really easy, even if you never did it before. Just follow Cython tutorial, and it's really, really easy to use and can increase the speed of your code a lot. It's basically, if you don't know Cython, it's just like Python code. You can think of it like Python code with static type declarations, so that it can kind of use this information to improve your code. Cython requires compilation, so Cython code, even if it looks like Python, it's being compiled into native code. So, and it's really easy because every Python code is already good Cython code. So you can already compile it, and it is already 2% faster than the CPython interpreter because it's basically expanding all the internal interpreter call without the interpreter loop. So it's already faster immediately. And then you just add one by one type declarations in your code, see the generated C code. One by one, you get speed. This is easy to use. Sorry, I'm missing a slide here. I suggest also to have a look into a graphical tool called RunSnakeRun. RunSnakeRun is a cprofile data analyzer. It's basically the graphical version of this pstats module, okay? With all the bell and whistles of graphical profiling tools. Okay, so if you are into user interface tools, you can try RunSnakeRun. It's really nice. Okay.
Can I interrupt?
Yes.
Just to say on the slide you showed recently.
Okay, perfect.
I'd also suggest throwing in shed skin to the mix.
Shed skin. Okay. So basically, what's your name? Sorry.
Ian Oswald.
Ian.
Ian Oswald. Okay. So basically, Ian is saying that this afternoon.
This afternoon in Pizza Margherita training.
Yeah.
2:30.
He has a very interesting training. I think I gave you 10-10 in my community voting. It's very interesting training about high-performance Python optimization coding, and it will show everything about this in detail. So this can be a teaser talk for you. My teaser talk to Ian is if you like this kind of stuff, you want to see how to optimize your code, use Cython, use Shedskin, which is another nice tool to compile your code, just go to the great Ian training this afternoon, okay? Thank you, Ian. Okay, last subject, last topic for today, how to debug C++ extensions. There is a nice answer to this question, which is by using a debugger, which is which is true, but it's not that easy. But it's not that easy to do because especially on Windows. So right now I'm going to focus mainly on Windows. Especially on Windows, there are lots of problems on getting things right to get to the point where you have your debugger set up with all the debug symbols in places, with not weird extraneous segfaults and stuff. So we are trying to show you how to do post-mortem debugging. So after a segfault, for instance, or step-by-step debugging into your code, which means you cannot step-by-step debug Python code. I mean, you can do that with the Python debugger, but you can step-by-step. What I mean here is step-by-step in C++ code, in code extensions, okay? So the main problems with Windows rely on, is basically tied to an old Microsoft choice to have different ABIs for different runtimes libraries, C runtime libraries. So basically when you switch between, for instance, debug and release builds in Visual Studio, debug and release builds have different ABI. If you don't know what, basically ABI means that you cannot mix-match dynamic libraries with different ABIs, otherwise you get different crashes from the one that you were debugging, which is not fun. And so the idea is that if you basically, you want to debug this module, if you just switch to debug mode for that only module, that module will change its ABI, so you cannot debug it together with the rest of your application, which is a problem because you don't want to recompile all your Word, which means Python itself, all your third-party extension you are using to debug, just to debug your extension, okay? If you have a look to the C runtime dynamic libraries under Windows, for instance, this is the MSVCR71D DLL, which is the debug C runtime for Visual Studio 7.1, which is .NET 2003, which is one CRT, okay? If you, for instance, switch to a release build, you are linking against the 71 without the DLL, which is incompatible, okay? So this can work only if all your libraries are using the same MSVCR library. To check if this is true or not in your application, I suggest to use on Windows this tool, which is Dependency Walker. It's a free AsimBeer tool that you can download. Or you can use a free AsimFreedom tools in PyInstallers, which is called BinDepend, a small tool on just command line. The Dependency Walker is a graphical tool. For instance, I'm running this against an old version of PyQt, and it will list all the DLL dependencies. You can see here that under Qt.pyd is depending on MSVCR71 DLL, so it's a release mode compiled across Visual Studio.NET 2003. When you run Python, and in a single process, you want just one instance of this family of DLL, okay? So if you have PyQt using this one, and then you recompile your third-party tool with the MSVCR 80 DLL because you're using a newer Visual Studio version, you are in trouble. Okay? So you need to use the same module against all the extensions, which means that it's not easy to just compile one extension and debug. You need to pay attention on how you are compiling it. This table will show you the correct MSVCR version for Python version. Since Python depends on MSVCR, you basically need to always use the same CRT library that the Python interpreter is using. Okay? So if you're using 2.6 plus newer versions, which is probably most of you are using, you need to use this Visual Studio version, which means all your third-party extensions need to be compiled with this one. Okay? This problem is being solved in Python 3, Python 3.2, because they are trying to introduce a fixed API for extensions. But since it's something that will happen in the future in real world, I will not explain this right now. But right now the problem is this: you always need to use the same CRT library. This is a small advertisement. There is a free MinGW build for Python developers in Developers open source website. Basically, it's a way to quickly recompile Python extensions, okay, without using Visual Studio, but using the correct MSVCR version. It's basically just a standard GCC build with a fancy installer that will set up everything correctly. You just tell which Python version you are using, and then you can use GCC to compile your extensions. Okay? Because standard MinGW builds use this one, MSVCRT DLL, so they are only compatible with Python 2.3. If you just download today MinGW and try to compile an extension for 2.6, it will not work. There are lots of tutorials on the webs on this. Okay, to get debug symbols, which is what you need to do debugging, usually, you need to compile in debug mode with Visual Studio, but with the same CRT of release version. Because either you recompile everything, and we don't want this, we want to use the standard Python interpreter. So the standard Python interpreter is using the release CRT version. So you want your extension to use the release CRT to be compatible, but with debug symbols. This is actually easy once you know it. Once you know this is your problem, it's very easy, because in Visual Studio you just need to go through the menus and find where the CRT is being defined. And in the debug build, you just need to switch to runtime multi-threaded release. Okay, so you probably have this fancy project made with Visual Studio. You just make sure that the debug build, the debug target is using multi-threaded release for runtime. This is the command line you want to use, which is /md, which is multi-threaded release. With this command line switch, you are telling Visual Studio to use this one, the right version of Visual Studio, of course. And then you want ZI, which is debug symbols, okay? Debug builds usually have this different switch, which means use the debug version, which we don't want to use. If you don't have the fancy Visual Studio project, you're just using these tools. In these tools, you cannot use --debug for two reasons. --debug was supposed to help you debugging your extension, but it's not, because --debug changes ABI 2 times in 2 different incompatible ways for the rest of the Python interpreter. One, it's because it's using the debug CRT for compiling the extension, which is totally useless unless you have a Python build, debug build, and everything in debug. And the second is --debug is activating this PyDebug mode, which is an internal debug mode made by CPython core developers for helping them develop Python. And --debug in these tools is activating this mode, which again is incompatible with everything else. So unless you compile everything in PyDebug mode, you cannot mix-match extensions, okay? So --debug in these tools is probably useless to most Python developers in the world. What you want to debug these tools in debug to compile an extension in debug mode just for having the symbols when you get a crash, you want to add these lines to these tools. You basically need to manually flip the correct switch on the command line. The same for GCC. Okay, GCC doesn't have this problem. But the same you need to do, GCC, I mean, under Linux, you can just specify the correct command line. In this way, you get your third-party extension compiled with the bug symbols, okay, but in a way that is fully compatible with the rest of your Python environment. You just have the bug symbols, which is what you probably wanted. And you can disable optimization, so your code is easier to inspect within a debugger, okay? We should probably eventually contribute something to these tools for this. If debug symbols in your DLL are not enough, you probably want debug symbols in Python itself sometimes. In Python 3.2, they are now shipping debug symbols on Windows as separate download, which is very nice. But if you're using older Python version, you need to recompile Python yourself, which is not hard because it's complicated to compile the whole Python distribution. But just the Python library, it's actually very easy to recompile. You just need to modify the standard debug target, as I was saying before, to switch the runtime CRT. But it's very easy to recompile so that you have debug symbols for Python and CPython as well. When you are at this point, so you have the debug symbols and you probably switched off optimization for the parts of code that you want to inspect. Then if you get a sigfold, you just press debug and you get the nice stack trace with all the symbols, which is what you were trying to achieve 2 hours ago. And another nice feature of Visual Studio in here is that if you just get a segfault, you press debug, jump into the debugger. If you save the generated workspace, you just save it, you can then modify the command line and rerun the whole application within a debugger. This is the easier way to do it. So you restart with F5, you put breakpoints, okay, in your C++ code, and you can debug. On Linux, the situation is much better because there is no this ABI CRT mess, and also because most distributions ship debug symbols for third-party libraries. So basically, if you're using, Python image library, Python pil, you just install the pil debug deb package, and you get the debug symbols. So when you get a crash, a dump, you just run it to GDB, and you get all the debug symbols, okay? You don't need to recompile anything. You just need to avoid the PyDebug mode, okay? So --debug still don't work on Linux because this PyDebug mode is incompatible. You still need to specify debugging command line documents to GCC within these tools, within setup.py, okay? And then a nice candy in Python 3.3 or 2, I don't remember, 3.3, there is this new module made by Victor Steiner available. It's called Fault Handler. Fault Handler is a nice module that you can just import and enable the way import anti-gravity works. And then when a segmentation fault is generated, which you can easily generate with this very handy function in Fault Handler, in case you want your application crash at random points, you just don't get a segmentation fault, but you get a Python traceback as well on standard error, which is really nice. Because you get a traceback at the point of the seg fault, which is interesting because at least to give you an idea, even without setting up the environment, the debugger, and everything, you get an idea of where your application is crashing. Probably you already have an idea, maybe not, maybe yes, I don't know, but still the traceback will confirm exactly at which point you are invoking C code that crashes. Okay? Fault Handler is really nice.
Might become the default, maybe?
Sorry? The default. Actually, I don't know. We should speak with Victor about this because I don't know if there are some side effects on enabling. I don't recall the discussion on the Python dev mailing list, but actually I will ask this because it's interesting. Another thing you can do is that on Unix, on Linux, you can register fault handler on a signal. So for instance, here I'm registering fault handler on the SIG user signal, SIG user 1 signal, and I'm saying that I want the traceback for all threads, and if I just need to send the SIG user signal to my process, and when I send it, it will display the traceback on the standard output. Okay? So at any time the process is running, I send it a SIG user signal, and it will dump the traceback for all threads. Okay? And another thing you can do is dump tracebacks later, and you say, I want all the tracebacks for all threads. It means in 10 seconds from now. Is also interesting function. Python free, but it's available on PyPy today for 2.x as well. So you can download it today and start using it, okay? Okay, I'm done.
We have very little time for questions, unfortunately.
Hello. You showed the trick with weakref and with the callback.
Yes.
Do you know why didn't they do it this way from the beginning with Dell?
Why do they do what?
Because Dell has its problems, right?
Dell, under Dell.
Yes.
Okay.
But you can emulate it with weakref without those problems.
No, it's not fully correct. You can emulate it, but your code will not work exactly the same way because you don't have a live reference to self available. You see, the live reference to self is the tricky part in Dell, because Dell is a finalizer, which is really funny because the object is going to die, but it will give you a live reference to self. So for instance, with this live reference, you can keep the object alive from Dell. You just append it to a global list, and the object stays live, even if it's being finalized. So that's the way, the weirdness in Dell. So you cannot do exactly the same with weakref, because weakref will never have a live reference to self. Otherwise, you have the nested loop. So the trick to use default argument is to pass what you need to the callback function, but not a full live reference to self.
You showed quite some ways about how to see all objects and etc. But my major problem with debugging this stuff is you see a lot of trees, but not the one you search for. Yeah. So is there some special procedure or trick how to get faster to the point to find the real leak in this big forest of lots of trees?
I actually don't know any. I actually don't know any solution for this problem. There is a tool called Maelie, I guess. Does anybody knows Maelie? Maelie, I think it's Maelie, something like that. It's on Launchpad. It's being developed by Barry Warsaw for debugging. What's the SCM name for Ubuntu? Bazaar, right. It's a debugging tool which is being developed to help them debug Bazaar, which has lots of memory leaks problems. So they have this big forest. Yeah, it's true. There are lots of memory leaks in Bazaar. And basically, there's nothing wrong with that because there are, short commands you run, even if it leaks 1 gigabyte of memory. When it's done, everything is collected. The problem is if it takes 5 hours and then the memory go into trash mode. That's the point when they need to debug it. And And Bazaar developers are debugging this Maeli, I think it is. If you search it on Launchpad, there are also a few blog posts that show you how to use it. So it's not really a mature tool. This is why I'm not.
Write it on a computer. Can you write it on a computer?
Yes.
I found it.
You found it on Launchpad?
M like Mike, E like Echo. Oops.
Miali, eh?
Mike, Echo, Lima, India, Alpha, Echo.
This one? No. Help me.
Not Emily.
Not Emily.
Mike, Echo, Lima, India, Alpha, Echo.
Alpha Echo. Okay, this one. And if you add this magic Google search blog post, you will find a few tutorials about it. I have never used it, so I'm just mentioning it.
I remember there are quite some such tools who should help you, but I tried some of them. Some don't even compile. Some are trying to help you, but you are still not finding a
This
problem.
is exactly, you see, I often want to figure out what is going on in my process while my process is consuming huge amounts of memory, 1 gigabytes, which is Bazaar. It also allows dramatically simplify the scanner, as I don't allocate Python object while trying to analyze Python object and memory allocation. So it's probably trying to target that problem.
I think I even tried it.
Okay, I never did actually, but you can try it if you want.
Any more questions?
Actually,
Median. Okay. Median.
okay. Some questions about the stuff you said about Windows debugging. Why don't you use these PDB files for extensions? You can just compile a release build with detached debug information, so you can debug a release build, and you can also mix and match those CRTD and CRT files if you make sure that your extension does not pass any buffers. You allocate with one and free with another. So
yeah,
it works usually.
If you make sure that you don't pass buffers or references to C objects, C runtime objects to other extensions, yes, you can probably mix match. But the point is that, in my opinion, it's not easy to make sure of that. If you wrote the third-party extension, yes, it's easy because you wrote it. But if you're debugging some other extension, it's hard to scan for this case. There is no automatic tool that tells you, yes, you can mix-match CRT extension. So the one good rule is never mix-match, because that always works.
Yes.
PDB symbols is correct, you can use them, but if you need to step-by-step debugging in release code, it's not always very good. So what I was showing is how to also disable, go to debug mode, so without optimization, but without changing CRT.
Yes,
okay,
that
just
works a
an
bit better.
extension. But you are correct. You can actually mix-match CRT if you make sure that a few checkpoint rules are matched.
This other feature you showed for Python 3.3, I think this done stack trace and core files on a signal or something. Does it work on Windows too? So you get a core file and basically something like that?
Python 2?
No, on Windows. Does it work on
sorry,
Windows?
the signal doesn't work on
No, signal of course not, but fault handler. Does that work on Windows?
Fault handler, yeah. Generally, it works on Windows. This one.
Yes.
This one works on Windows as well.
Okay, good.
This signal is Unix only.
Yes, and did you ever use things like wall grind for the C part? So to debug C extensions and stuff like reference leaks there.
Sorry, I didn't.
Wall grind, using wall grind to
wall grind.
trace stuff like that.
No, yeah. Actually, it's a good suggestion. You can try wall grind to debug this kind of memory leaks. And for wall grind, there is if you want to use Valgrind on Python extension, you can do that. It's a really nice tool. There is just one problem. You need to find a specific Python suppression file. Suppression files are definition for Valgrind that tells him to skip a few false positives in the CPython interpreter. Because if you just run Valgrind on Python, it looks like it's leaking like hell, everything, but it's just false positives for the way the Python object collector works. So you need to get this Valgrind Python suppression file, something like that, which is actually part of the Python source code. Okay, but if you Google it, you will download it. Then you, when you run Valgrind, you specify this file, and then you remove all those false positives, and you see the real memory leaks. Okay.
There's no more time for questions. It's coffee break time. Remember to get